Hello friends, welcome you all to the next lecture of the JC eConnect series of video lectures. We are dealing with Module 5 Kinematics, Motion under Gravity. This is the last lecture for this topic. Yesterday we have gone through a few examples. Let me continue with the further examples. I hope that you have solved those examples, and if you have any doubts, I hope that you will get back to us in time. So now let's start with the next example. In this example, it is given that a ball is thrown vertically into air at a velocity of 36 meter per second. After 3 seconds, another ball is thrown vertically up with the initial velocity such that the second ball has to pass the first ball from the ground at 30 meters. So here scenario is pretty much clear. You are throwing ball number 1 with an initial velocity of 36 meter per second. You are taking a gap of 3 seconds. After 3 seconds you are throwing the second ball. Then the second ball has to pass the first ball at a height of 30 meters from the ground. So if the second ball has to pass the first ball at a height of 30 meters, with what velocity the second ball must be thrown? This is what we have to determine. Okay, this is what we have to determine. That is u for the second ball we have to determine. So let's start with the example. Now the distance travelled by both the balls is same because we are analyzing up to a height of 30 meters only. So S or H, whatever you want you can take, is equal to 30 meters for both the balls. Now let t be the time taken by the first ball to reach a height of 30 meters. Okay, small t be the time taken by the first ball to reach a height of 30 meters. Now as we are throwing the second ball with a delay of 3 seconds, okay, with a delay of 3 seconds, the time taken by the second ball to reach that height, let that be t plus 3. Okay, because we are throwing the second ball with a delay. So let our time be t plus 3. Now once we consider the first ball, initial velocity is 36 meters per second, distance travelled is 30 meters. So using the equation S is equal to ut minus half gt square, I have used the minus sign because the ball is moving upwards. Substituting the values, we get a quadratic equation. So this quadratic equation has to be solved by you all for getting the value of t. So by solving the quadratic equation, we get t as 6.38 seconds. Okay, we get the time t as 6.38 seconds. That means the first ball, which is thrown with a velocity of 36 meter per second, reaches the height of 30 meters in time equal to 6.38 seconds. Now let us go for analyzing the second ball. Now as per our equation, time required for the second ball to reach the same height is t plus 3 because that ball has been thrown with a delay of 3 seconds. Therefore the time required for the second ball is equal to 6.38 plus 3, which gives us an answer of 9.38 second. Now in this case we know the time but we don't know the initial velocity. Hence again using the same equation, S is equal to ut minus half gt square, substituting S, which is 30. Remember S is 30, that is distance travelled by both the balls is 30 meters from the ground. U is unknown. We have found out t as 9.38, and substituting and solving for u, we get the answer as 49.207 meter per second. Therefore we have to throw the second ball with a velocity of 49.2 meter per second so that it crosses the first ball at a height of 30 meters from the ground. So in this example, while analyzing ball 1, we found out time t. We used that value of t while analyzing ball 2 and we found the initial velocity of the second ball. Hope this example is clear. Let's move to the next example. This is a bit interesting example. Okay, so let's go to the example. A stone is dropped down a well with no initial velocity and after 4.5 seconds a splash is heard. Then a second stone is thrown downwards with the initial velocity V0 and the splash is heard after 4 seconds. If the velocity of the sound is constant at 336 meter per second, determine the initial velocity of the second sound. Okay, determine the initial velocity of the second sound. Sorry, initial velocity of the second sound it is written, but it should be initial velocity of the second stone which is thrown. Now, important things to be understood from the example. The first stone which is dropped is not thrown, it is just dropped. That means it has no initial velocity, it is what we call as a free fall. Okay, this is the important thing to be noted, that the first stone is dropped, but whereas the second stone is thrown. So when you throw a stone, it will have some initial velocity. So that is unknown in this example. Again, this example has two parts. First is with respect to first stone, second part is respect to the second stone. Now splash, what is a splash? It is the sound which is heard when we throw something in water, and I think you all must have done this thing. Okay, you must have thrown a lot of stones in the water. So now let's start the analysis. So let us consider the first stone. So now first I will tell you the action of first stone. What happens? Say it is at the top of the well, point A, then it reaches the surface of the water, point B. When the stone reaches the surface of the water, a splash is heard. That splash travels, or that sound or that noise produced travels from the surface of the water to the top of the well where you are standing and you hear it. Okay, is that clear? Again I will repeat, we don't throw the stone here, the stone falls from top of the well, it reaches the surface of the well, one path is covered. Secondly, the sound is developed when it reaches the surface of the water, and that sound travels back again from the surface of the water to the top of the well where we are standing and we can hear the splash. This entire process takes place in 4.5 seconds. Okay, this entire thing happens in 4.5 seconds. That is the stone moving from top to bottom and the sound coming from bottom to top. Entire process takes place in 4.5 seconds. Understanding this is the key in this example. Now, if we say let small t be the time taken by the stone to reach the water surface, that is the first path. Time taken by first stone to reach the water surface, let it be small t. Then the time available for the sound to come from water surface to the top can be written as 4.5 minus t, because as I told, entire process takes place in how much time? 4.5. First time is small t, therefore the second time, that is sound reaching your ear from the water surface, can be written as 4.5 minus t seconds. Now this becomes the core of this problem. Understanding this becomes very important. Okay. Now distance travelled from top surface of the well to the surface of the water. Okay, distance travels from top surface of the well to the surface of the water. Let this be h or s, whatever term you use, but use the constant term. So we can write the equation h equal to ut plus half gt square. So this is the stone falling. We are not throwing the stone, stone is falling. So initial velocity u becomes 0. Therefore, h is equal to half gt square. Let this be equation 1. Now for the sound, distance travelled by the sound is the same as the distance travelled by the stone, because stone is moving from top of the well to the water surface. Sound is coming from the water surface to the top of the well. So this also becomes h. Therefore, distance travelled is equal to velocity into time. Velocity of sound is given as 336 multiplied by time of sound. We have taken it as 4.5 minus t. Therefore, we have two equations for h. One equation is the stone falling from top to the water surface. Second equation is for the sound which is generated on the water surface to reach the top of the well. So, in both the cases, as the distance travelled is same, we can equate 1 and 2. Therefore, equating 1 and 2, we get a quadratic equation, and by solving the quadratic equation for t, we get t is equal to 4.238 seconds. We get t is equal to what? 4.238 seconds. Now either you can solve with the equation or you can use your calculator. Now therefore, out of this 4.238 seconds, what we have got? 4.5 minus 4.238 gives 0.262. Now what is 0.262? It is the time required by the noise produced to reach from the surface of the water to you, and you are standing at the top of the well. So it's a very small time. Okay, it's a very small time. When you take 4.5 seconds, entire process is completed. For the stone to reach water, it takes 4.328 seconds, whereas for the sound to reach from the water surface to the top of the well, it takes only 0.262 seconds. Now once we get this, okay, once we get this value, we can get h. Okay, we can get the value of h very easily. Okay, we can get the value of h very easily. So substituting this in the equation for h, okay, substituting this in the equation for h, that is v into t, h is equal to v into t. V is velocity of sound, which is 336, t is time of sound, which we have got as 0.262. We get h as 88.03 meters. Now that means the water level in the well from the top of the well is at a height of 88.03 meters. Okay, so from the first part, or from the analysis of first stone which is freely falling, we are able to get the height or depth at which water is there in the well from the top. Now let's come for the analysis of second stone. Now second stone is not freely falling, it is thrown. Okay, it is thrown, and in this case, as it is thrown, that means it will be moving a bit faster than the free fall. Hence we are hearing a splash noise or the sound of the splash after 4 seconds. Okay, so applying same principles as we have applied in the previous case, here let t be again the time for the second stone. Don't confuse it with the first t. First stone analysis is over. Here we are considering only the second stone analysis. Okay, let t be the time for the second stone. Therefore, similarly as previous, time required for the sound to travel from the water surface to the top of the well will be equal to 4 minus t. Okay, therefore the distance travelled, okay, distance travelled, s for the sound will be equal to v, that is velocity of sound, into time. Okay, velocity of sound into time, that is v into bracket 4 minus t. Now s is nothing but h, that is the depth at which water is there, that is the distance with the stone travels, which we have got as 88.03. Substituting this 88.03 from the previous page, okay, from the previous workout, and V value is given as 336, 4 is there, and T we have to find. Equating, we get T value as 3.738 seconds. That means in the second stone takes 3.738 seconds to reach the water surface. Therefore, from the equation, H is equal to Vt plus half Gt square. Here H is nothing but S, which is the depth at which water lies, that is 88.03. V0 is the velocity with which that second stone is thrown, we don't know. T is the time taken by the second stone to reach the water surface, which we have found out as 3.738 half into G into T square. We get V0 as 5.215 meter per second. That means if we are able to throw the stone, second stone, with a velocity, initial velocity of 5.215 meter per second, then we will be able to hear the splash at 4 seconds. Okay, after 4 seconds we will be able to hear the splash. Whereas when that stone is free falling, that is with zero initial velocity, same splash noise we can hear after 4.5 seconds. That means if the stone is thrown with the initial velocity, we can hear the sound of the splash early, whereas if the stone is free falling, that is without any initial velocity, we hear the sound of the splash a bit late. Okay, so this is all about motion under gravity. Okay, we have solved the examples. By this we conclude the kinematics part of your 5th module. Hope you all have started to solve. I know it is not that easy, but still it will help us when we restart the classes. So on a writer note, all of you must have seen both of these cartoons. One is everyone's favorite Tom and Jerry. Gravity does not work until you look down, but this is wrong. We have solved examples on it, and now we all know as an engineer how the gravity works. Thank you all. Hope you all of you are taking the necessary care and precautions. Hope you all are healthy, fit and fine. So I'll conclude with this. Thank you.